Welcome back to the channel. If you've been here before, you know that I do animations and 3D models of mechanical systems, and I use those animations to explain the operating principles and the history of those systems. I recently did a series on helicopter aerodynamics and control. I'm not done with that series. I still plan to make more helicopter videos, but I started work on a 3D model of a tiltrotor. This is still a work in progress, and as I did for the Black Hawk helicopter series, I'm going to post videos showing the incremental progress of this build. These incremental videos are helpful to me because I'm able to use viewer comments to modify the design. Your comments also tell me what you want to see in future videos. I plan to focus the animation of the tiltrotor on the drive system and the flight controls, but I also added the wing and an ornamental design of the fuselage and tail. Unlike my helicopter videos, I think it's harder to tell what you're looking at with a tiltrotor if I don't show these features. As of today, the only animated components are the prop rotors and the pylon conversion system. Right now this model lives in computer-aided design software. In the future, I'll export this to Blender before I start the more serious animations. With the Black Hawk model, my goal was to faithfully reproduce as much of the actual UH-60 design as I could. I was able to do this because there's so much public source technical data available on the Black Hawk. But when compared to the H-60, there just isn't as much public technical data available for current and past tiltrotors. So the design you see on the screen isn't representative of any one of these aircraft. It's not meant to copy an existing design, it's simply meant to show the configuration of existing tiltrotors so I can explain some operating principles of these aircraft. In today's video, I'll cover some history of tiltrotors and then I'll talk about the configuration you see on the screen. The technical references I used to create this design are listed in the video description. I keep calling this a tiltrotor, but according to the FAA, the U.S. Aviation Authority, there isn't an aircraft category called a tiltrotor. In the United States, powered aircraft are defined as either airplanes, rotorcraft, or powered lift. Tiltrotors fit into the powered lift category because the wings produce the lift when the drive system is in this position, and the rotors produce the lift when the drive system is in this position. Tiltrotors are not a new idea. The first concepts for these aircraft date back to the 1930s, and they first started flying in the 1950s. Here's an image of the Baynes tiltrotor from 1938, and here's an image of the Platt-LePage design. Platt's tiltrotor was likely near in time to Baynes. The Platt-LePage company was active from 1938 to 1947, but Platt didn't file this patent until 1950. Bell ended up licensing this patent from Platt, and this may be why he patented it after his company ceased operations. While tiltrotors are not a new idea, they've seen renewed interest in the 21st century. Many current companies are advancing this technology along with new concepts for simplified vehicle control, distributed electric propulsion, and urban air mobility. Some of these new powered lift designs might be better described as tilt props or tilt ducts. But for this video, I'm focusing on a design that uses swashplate controlled rotors and turbine engines. The first of these tiltrotors with a swashplate controlled rotor was the Trancendental 1G. This was followed by the Bell XV3, and then under NASA leadership, the Bell XV15. So far I've mentioned 3 U.S. aircraft companies involved in tiltrotor development: Platt-LePage, Trancendental, and Bell. A common thread between all of these companies was an engineer named Bob Lichten. Lichten worked at all 3 of these companies, and he is considered the father of the modern tiltrotor. In this photo, Mr. Lichten is seen on your left accepting the Vertical Flight Society's Clement Award after the XV3 became the first tiltrotor to demonstrate full conversion flight in 1958. After the development of these X-planes, the next 3 tiltrotors were produced in production configurations for sale to customers. These are the Bell and later the Bell Boeing V-22 Osprey, the Augusta Westland 609, which started its life as the Bell Boeing 609, and finally the Bell V-280 Valor. If you're interested in reading more about the development of tiltrotors, a good resource is The History of the XV-15 Tiltrotor Research Aircraft. This book is a free download from NASA. Not only does it talk about the XV-15, it also talks about the market dynamics and research that took place in the early 20th century, well before the first flight of a practical tiltrotor. Another worthwhile resource is Richard Whittle's book, The Dream Machine. This book focuses on the development of the V-22 Osprey, but the first few chapters wind the clock all the way back to the origin story of the tiltrotor in the 1930s. And again, my 3D model isn't intended to be a copy of any of these existing designs, but I use design elements from all of them to animate how these aircraft operate. I'll go over the configuration of what's on the screen and make a few references back to these current and past designs. In this design, the wing remains stationary and the rotors, engines, and gearboxes tilt forward and aft to affect the transition between fast flight and slow flight. This concept of moving both the engines and the gearboxes, it's not universal amongst all tilt rotors. The early tilt rotors, the 1G and the XV3, use stationary engines, as does the Bell V280 Valor, which is the most recent design. I'll hide the gearboxes in the nacelle to show the mechanism used to transition from hover to forward flight. This is a dual recirculating ball screw mechanism. The V-22, the AW609, and possibly some of the other tiltrotor designs use this type of a mechanism. And here's a patent image. Bell owns this patent, showing the cross-section of how this dual ball screw actuator works. I actually tried to make my design simpler by using a single-stage ball screw, but I found that it wasn't geometrically possible. A single screw was just too long. When the nacelles were positioned for wing-borne flight, the screw was impractically too far ahead of the leading edge of the wing. It would have interfered with the prop rotors. The CAD model is a work in progress. I'm sure you noticed the top of the conversion actuator is not connected to the pylon conversion arm. I'll correct this after I export the design into the animation software. What you see on the screen is computer-aided design, and surprisingly, animation software has more capability than CAD for connecting and animating mechanical components. I can drag these into the correct positions in the CAD to verify the dimensions, but animating them is pretty convoluted, whereas in Blender it's almost trivial to rig and animate the mechanical connections. The range of motion of this pylon conversion system is from 0 degrees in wing-borne flight to 97 degrees in thrust-borne flight. Motion past the vertical in a hover is useful for a few things. It allows more effective deceleration on the approach to hover, and it allows the pilot to decouple hover position and hover attitude, which is useful for landing on sloping terrain. This tiltrotor uses 5 gearboxes to transfer power from the engines to the drive system. There is a prop rotor gearbox at each wingtip. This gearbox connects the engine to its onside prop rotor through a 3-stage gear reduction. This gearbox takes the engine output power at 30,000 RPM and delivers that power to the prop rotor at 500 RPM. This is a higher RPM than V-22 prop rotor blades, but my design has a smaller wingspan than the Osprey. In this regard, there are a few important design considerations for tilt rotors. In a hover, you want the prop rotors to be as large as possible for better hover efficiency, and you don't want them to hit the fuselage in forward flight, and you never want the rotor tips in the prop rotor system to go transonic. A smaller wingspan necessitates smaller diameter rotors, and this means their RPM can be higher without seeing transonic tip Mach effects. My design goal for what you see on the screen was for these rotors to have a tip speed of 70% Mach 1 at standard sea level conditions, and this worked out to 506 RPM with a 59-to-1 gear reduction from the engine to the rotor. Aft of the prop rotor gearboxes are the tilt axis gearboxes. These have an important function during one engine in operative flight. If the onside engine fails, power is automatically transferred from the good engine side through the tilt axis gearboxes and across the wing interconnect drive shaft to the prop rotor gearbox on the side with the failed engine. This is an important safety feature. Tilt rotors are fault tolerant of engine failures, but they are not fault tolerant of thrust asymmetry. This is different from multi-engine airplanes. Airplanes are capable of flying when one side of the aircraft loses thrust. This is because this thrust is designed to be as close as possible to the center line of the aircraft, and because the engines, when compared to a hover-capable tilt rotor, simply don't produce that much thrust. But in tilt rotors, where the thrust must be placed far from the aircraft's centerline due to the size of the prop rotors, and where each side produces thrust roughly equal to the weight of the aircraft, it's essential that both side prop rotors always have power. The wing interconnect driveshaft is the means to provide continuous power to both prop rotors regardless of the operating state of the engines. If you think I just misspoke, I did not. Power is provided to the rotors in all engine-out flight by autorotative forces on the blades. Unlike airplanes, tilt-rotor pilots don't feather their props when an engine fails. These rotors always turn in flight. Power comes from the engines when they are operating and from autorotative forces during all engine-out flight. The 21st century may be challenging this core design assumption of these twin-engine tilt rotors. Some of the distributed electric propulsion designs forego the mechanical safety advantage of connected rotors by adding motor redundancy to the design. One design concept is that when one electric motor fails, they can intentionally mirror that failure to the other side in order to retain symmetric thrust. The fifth gearbox in this tilt rotor is the mid-wing gearbox. You can see the wing has forward sweep and dihedral. Dihedral is for stability, specifically rolling moment due to side slip, and forward sweep is needed to give the rotor blades adequate clearance from the wing leading edges. This is a swash plate controlled rotor, so the rotor blades flap in order to control the aircraft. But sweep and dihedral introduce a geometric challenge of passing drive power from one side of the aircraft to the other. You may think the purpose of the mid-wing gearbox is to facilitate the change in direction of the interconnect driveshaft. In fact, the gearbox did function to change direction of the driveshaft in the XV-15. But with the V-22, the mid-wing gearbox doesn't provide any direction change. Instead, its purpose is only to extract power from the drive system to power hydraulic and electric service for the aircraft. The angular misalignment of the wing driveshaft, to include the accommodation for wing flex, is taken up by these discs in the drive system. These are called multiple element convoluted diaphragm couplings, and each coupling is capable of deforming to accommodate up to 3.5 degrees of misalignment. I modeled a forward wing sweep of 6 degrees, so the 4 couplings provide more than twice the needed change in direction. I know the V-22 Osprey has more of these couplings, but I limited my model to 4 only to simplify the work of animating these deforming components. Let's talk briefly about the rotor system. You can see this is incomplete as of this video. I haven't modeled the rotor controls and the hubs are incomplete. The hub for this design will be a 3-bladed teetering hub with an elastomeric hub spring, and the blades will have negative pitch flap coupling, which means when the blades flap away from neutral, they will also increase pitch. This is the same design as the XV-15 and the V-22. And this is a super interesting piece of the development of the technology of tilt rotors. The very first tilt rotor started with a fully articulated rotor system. Then it became a 2-bladed teetering rotor system with positive pitch flap coupling. And they finally ended up with the 3-bladed teetering rotor with negative pitch flap coupling. As for the blades themselves, these prop rotors are counter-rotating. The left side rotates counterclockwise and the right side rotates clockwise. So the left side blades are mirror images of the right side blades, and they are not interchangeable. I used a constant airfoil section for the blades, although I vary the section thickness and the chord. Each blade has 34 degrees of twist. The high twist of tilt rotor blades is an optimization for fast wingborne flight, and this amount of twist absolutely degrades hover performance. If you were to optimize these blades for hover, they would be twisted somewhere probably between 12 and 18 degrees. And this is characteristic of many design features in tilt rotors. Engineers have to look for a compromise between fast wingborne flight and slow thrustborne flight. Tilt rotors are not the best airplanes, and they are not the best helicopters, but they are best at flying 300 knots to and from places that are not airports, and that's what sets them apart from these other less capable aircraft. This is all I have for you in today's video. In my next video, I plan to have this model exported into the animation software with a functioning model of the drive system and the pylon conversion system. If you like this content, if you want to see more videos like this, please like, subscribe, and comment. I'll see you on the next video.